From ancient Rome to modern skylines, concrete has built empires and shaped civilizations. But today, that legacy is cracking, fracturing not just our structures, but the very environment we depend on. Concrete, the most used material on Earth after water, with over 4 billion tons produced every year. Yet, it carries a hidden burden: cement. A primary ingredient of concrete is responsible of nearly 8% of global carbon dioxide emissions, impacting ice caps and coastlines. Roads, bridges, buildings, each structure carries an unseen footprint. The question is, can we build a future where concrete is part of the solution, not the problem?
The answer lies in innovation, partially replacing cement with industrial byproducts, reducing our reliance on carbon-intensive materials. Fly ash is a widely used supplementary cementitious materials derived from coal combustion in power plants. Its fine, pozzolanic particles enhance concrete workability, durability, and long-term strength while reducing the demand for traditional cement. Silica fume is an ultrafine byproduct of silicon and ferrosilicon production, known for its high pozzolanic reactivity. When added to concrete, it significantly enhances strength, reduces permeability, and improves resistance to chemical attacks. Ground granulated blast furnace slag is a supplementary cementitious material obtained from the steel industry formed by quenching molten slag. It acts as a partial cement replacement, improving durability, reducing hydration, and drastically cutting carbon emissions. Selecting the right combination isn't discovered by guesswork. It is determined through precision and careful calculation.
We start by developing two distinct concrete scenarios identified as SCS and BCS. For the base case scenario, uses traditional Portland cement with aggregates for the concrete mixture. However, for the alternate case scenario or SCS, we incorporate supplementary cementitious materials, namely coal fly ash, silica fume, and granulated blast furnace slag. We ensure realistic and region-specific modeling and best quality control with the careful consideration of transportation methods, road, rail, and waterways. For this, we picked two cement sources with the best possible quality, Bosundhara cement and INSI cement. Both the sources have minimum roadway and maximum waterway, as well as they are both located in Narayanganj. The fine aggregate and the coarse aggregate both are collected from Bholaganj Sylhet. In the base case, the mix consists of 419 kg of cement, about 17.2% of the total volume. The aggregate content is the same in both cases, where fine aggregate is 853 kg and coarse aggregate is 995 kg per meter cube. This careful composition ensures that over 75% of the total mass comes from aggregate, aligning with the ACI sustainability goals. The SCMs, coal fly ash, silica fume, and GGBS are collected from the predefined locations, so their distance are fixed. In the alternate case, we replace 40% of the binder with SCMs, 6.25% coal fly ash, and the remaining is silica fume, while maintaining total mass and water binder ratio of 0.4. Through multiple combinations, we found that using roadway and waterway transport for all materials and using the cement from Bosundhara significantly minimizes emissions, especially regarding global warming potential.
To design the optimal EcoConcrete mix, we initiated a structured three-phase process. Phase 1, trial dataset generation. Phase 2, statistical analysis and search algorithm application. And finally, validation and selection of the most sustainable and durable concrete mix. We explored a wide range of percentages for fly ash, blast furnace slag, and silica fume, targeting a total of 40% SCM substitution. Every combination was analyzed to determine the service life durability score using Life-365 and the environmental impact reduction using EcoConcrete calculation tool for all alternative case scenarios. Here is the sample dataset that we found using Life-365. As we decreased silica fume and increased blast furnace slag for a specific fly ash percentage, we noticed a drop in durability, highlighting the importance of balance in SCM selection. Here is the sample dataset that we found using EcoConcrete calculation tool. Here we could notice for a specific fly ash percentage, the environmental impact reduction percentage is proportional to the blast furnace slag percentage and inversely proportional to the percentage of silica fume. To understand the relationship between performance indicators, we analyzed Pearson correlation coefficients among variables like fly ash, blast furnace slag, silica fume, durability score, and environmental impact reduction percentage. We observed strong positive and negative correlations, but with so many variables and constraints, manually finding the optimum SCM mix is both tiresome and inefficient.
In our efforts to determine the optimal mix ratio of supplementary cementitious material, we adopted a multi-analytical approach. We categorized our methods into three main groups: search algorithms, statistical analysis, and machine learning algorithms. After running multiple optimization techniques, we compiled this comparative table showing the optimal mix ratio and corresponding durability score and EIR reduction percentage. Also, we have the validation from the software. In this comparative approach, we didn't allow null contribution for each SCM. But in this comparative approaches, we allowed null contribution for each SCM. We can see that we achieved a superior durability score of 3.15, but it failed the EI criterion with only 14.7% reduction, making it non-compliant with the sustainability threshold. Instead, we choose the closest mix ratio with 3.06% durability score and 15.1% EIR. And this is the software validation and service life report. And this is the EIR report. And this is our final optimized mix ratio. Using this optimized mix ratio, we calculated each element of our ACS mixture.
Our optimized mix achieves a 15.1% overall environmental impact reduction. Notably, we reduced global warming potential by 30%, ozone depletion by 23.8%, and fossil fuel use by 25.9%. Reductions in global warming and fossil fuel depletion are a direct result of lower cement use and optimized transportation. As studies show, silica foam has 4 times the carcinogenic and ecotoxic potential of cement. That's why we limited its content to just 3.75% to ensure environmental safety.
To wrap up, EcoConcrete is not just an alternative material, it's a powerful tool in our journey towards a more sustainable future. Let's move forward, not just by building structure, but building responsibility for our planet and people. Thank you.